Physics students, good afternoon. Mr. Hooke here. Today in this video, we're going to be looking at a problem involving spring force, one of the concepts that was related to what we began discussing in Unit 6. This problem does show up on your homework assignment number 8. This is problem number 2. We're going to look at stretching a spring and using a force to find the spring constant. So, question 2 says this, the first of a two-part question. A slingshot consists of a light leather cup attached between two rubber bands. It takes a force of 29 newtons to stretch the bands 1.5 centimeters. And this question is asking us, what is the equivalent spring constant of the rubber bands? So here, this question number 2, we want to find a spring constant. We're given a force and a displacement. So if you remember from what we discussed related to Unit 6, our spring force is equal to negative K times delta x, where K is our spring constant and delta x is our displacement, how much our spring is being displaced from its original length. Now here, we can still use this approach for dealing with a rubber band because as we saw in the lab, the properties for springs and rubber bands are mostly the same, that elastic force. So we're given some values here. We're told our force that we're applying onto the spring, I believe, was 29 newtons. As with the problem here, your numbers are going to be different on your assignment, but the process will stay the same. And then we're told the bands stretch 1.5 centimeters. Our delta x is 1.5 centimeters. Now, don't forget, when we're dealing with this spring force, we need to make sure we're in SI units. So we're going to divide that 1.5 by 100, or move our decimal 2 places to the left, which will give us a value of 0.015 meters. So we have the variables that we need, and we're going to plug in and solve for our spring constant. Now, as we discussed in class, the spring constant is a scalar. And we're not really told here much about the direction that our rubber bands are being displaced. And so we'll assume that they're being displaced down. We're going to launch this object up because our value for spring constant is always going to be a positive value. It's a scalar and not a vector. So we'll plug in for our spring force, FSP, 29 newtons. I'll rewrite our equation just momentarily. So FSP, our force, was 29 newtons is equal to negative K times delta x. And we'll assume that delta x is negative. We're changing our length in the negative direction. 0.015 meters. Okay? So we want to get our constant by itself, and we'll just need to do a little bit of algebra here. We're going to divide by 0.015 meters on both sides of our equation. Because we have a negative value in 2 places, a negative times a negative will give us a positive value. So we'll divide by our displacement, 0.015 meters, on both sides of our equation. So our value on the right-hand side will cancel out, and we'll be left with a value for our constant of 29 newtons, plug that in, divided by 0.015 meters. Now we're going to get a pretty high value here. K is, let's see, 1,933.3 newtons per meter. So we're dealing here with an extremely stiff spring. Okay? Just to double check that we're correct, I'll look at the key here. Now 1,933.3, so we're good to go. So that's how we would approach solving for our spring constant. And as long as we have the force that's being applied onto that spring or rubber band, as well as how much the rubber band is being displaced, we can solve for our constant. And so, remember, don't forget, we need to pay close attention to our units here. Our delta x, the displacement, needs to be in meters, not centimeters. Everything else is good to go. Hopefully this will get you started. Just a basic setup of solving for that spring constant. Good luck.